Guys, how's everybody today? You guys are getting more snow, I hear. Is it snowing right now? No? Is it supposed to?
Not that I'm aware of.
Really? I thought I got some notification from my my complex at home that everybody needs to move their cars.
I saw they put some like salt, but I don't think there's gonna be like a lot of snow.
Yeah, I think it's supposed to snow tonight.
I'm just checking for you. It looks like snow and sleet tonight, like around 6 or 7 for you guys. But then there's like a 92% chance at 9 p.m. and it's going to continue going until tomorrow morning. So I'm in Florida and it's 79 degrees right now. So not to brag or anything, but I'm taking care of someone all day, so it's not like I'm out in it though. All right, so let's get started. This is, oh wait, let me share my screen. Didn't do that yet. All right, guys, I'd like to see your faces, remember. Okay, so what I'm asking you to do here is just use some of the things that you know about moving a graph around the coordinate plane. And I'm going to give you a hint. I just want you to kind of think of like where these graphs might be. So let's see, here's my hint. So this original graph is y equals x squared, right? So this is y equals x squared. So if you took that function x squared and added 2 to it, you would end up getting that same function, but the parabola would just be moved up 2 units. So what do you think would happen if you put something inside that function and you were adding 2? How would the parabola move around the coordinate plane? Anybody?
Left 2.
Left 2, yeah, great job, Joey, absolutely. If it's inside the function, it's going to move in the opposite direction, remember? If it's outside the function, it'll do what you think it would do, right? If it's outside the function, it's vertical movement. If it's inside the function, it's horizontal movement. So yeah, absolutely. This would go left 2 because it's inside the function. So it would look something like this. And these are just sketches. All right, what about inside the function, but we're doing x minus 2 this time?
It shifts 2 units to the right.
Yeah, very good. So it would just go to the right, which is kind of the opposite of what you think it might do, right? But that's because it's inside the function. That's how you remember that. All right, what do you guys think? And maybe you remember this, maybe you don't, from, oops, sorry, from algebra 2, like what happens to a function when you multiply it on the outside?
Does it widen?
Oh, you're close. It does do something, but it doesn't widen it. It makes it skinnier, Kevin. So it would be even skinnier than the original, right? Because it's going to make, it's kind of like a slope, right? So a slope of a whole number is going to make a line steeper than the slope of, say, a fraction. Does that make sense? Yeah. So that's going to make it skinnier. And then what do you think will happen if you multiply it on the inside of the function by 2?
Widen.
It doesn't actually widen, no. If you multiply the outside by a fraction, then it would widen, right? But what ends up happening is it looks really similar to that yellow graph here, because it's kind of the same thing. And I included this in the notes for you. They call it when you multiply a function on the outside by like 2, you're going to vertically stretch it by 2, right? And that's kind of like the analogy with the steeper slope, right? But if you, it's kind of similar because what you're doing to a parabola is they call it you're horizontally squishing it. Vertically stretching something and horizontally squishing it is very, very similar, right? And then I just so that you have these decent notes here. And I want to, I'm going to put this in the notes for you guys. So this is being shifted up by 2. That's the hint that I gave you in the beginning. And then these are the 2 that you guys got. Great job on that. And then here, see the difference here. If you multiply a function on the outside, it's going to vertically stretch it like this, right? Which is similar to horizontally squishing something. So they're going to look very similar. All right, so that's kind of a review of the last part of 1.8. We're going to move on to 1.9 now. And when I print these out and post these notes, I will post this stuff for you. So you don't have to worry about copying it down. Okay, so now we're going to talk about proportionality and power functions. Down here at the definition, a power function, let's see if I can make this a little bigger for you. A power function is of the form f of x equals c, x to the n, when this is important, where c is the constant called the proportionality constant. So I went and dug up these pictures from the internet. When you learned about something being directly proportional and inversely proportional back in like algebra 2 or maybe college algebra, you learned it with like y is equal to kx. Well, since we're in this applied calculus, I wanted to just show you how you might remember this. But once we move to applied calculus, we're going to use f of x is equal to c, where c is your constant of proportionality, right? What every other algebra book uses a k for, they're using a c. And then it's just x to some variable, right? So when that variable is positive, you have direct proportion, okay? So if n is greater than 0, we have direct. And then the same function here, we're going to use, oops. And if n is less than 0 or a negative number, you're going to have inverse. So this is what I'm putting these in here because this is how you learned it back in algebra 2, right? Direct proportions and inverse direct. Here we're saying that there is a constant of proportionality here and here, C. The difference is whether or not the exponent is positive or negative. We're going to go over some exponential rules and you'll see why, like, where does that come in, right? Okay. So here's the first example. they want you to write a formula for heart mass as a function of body mass. So I'm going to start out with what you guys know is y equals kx. And then this is saying that that y is proportional to x, right? So here we want heart mass is proportional to body mass by constant k. Okay, so we did it. We wrote a formula, right? And also another thing I want to remind you here, you see how it doesn't tell you if it's direct or proportional, or sorry, it doesn't say whether it's direct or inversely proportional. And here's the thing on that. Unless they directly say it is inversely proportional, then it's always assumed to be direct proportional, okay? So, how do I want to say this? Directly is implied unless inverse is stated. So you can always assume that I'm asking you for direct proportion formula unless I say otherwise. Okay, so we wrote the formula. Now they give us information. Now body mass is 70 and heart mass is 0.42. We're going to use that information to find the constant of proportionality, which is the K value. All right, so we're going to start with our formula, H equals KB. We're going to plug in what we know, which is 0.42 for heart mass. There's the constant of proportionality, and 70 for that. Now, all we're going to do here is just solve for K by dividing both sides by 70. So K is equal to 0.006. So now that we have the K value, what that does is that gives us a better formula that we can estimate the heart mass of something else. So if I start with H equals KB, where K is equal to 0.006 from up here, then H would equal 0.006 times the body mass of 650, which if you put this in your calculator, you would get 3.9 kilograms. So from this up here, we end up getting a formula, H is equal to 0.006 times the body mass. So then I just gave you the body mass was 650 kilograms. So then the heart mass would be 3.9 kilograms. Any questions?
Could you go back up? I missed the inverse
Sure,
proportion.
Sean. Sure, Sean. No
Thanks.
problem. I'm sure other people missed it too, so don't feel bad about asking. Got you down.
Yeah, so I have a question. Is that CX raised to the power? Is that like another version of the direct proportional formula?
It is, and I'm going to get you there, but I want to use the formula you guys are more familiar with first, And then I'm going to get you to that power function. Yeah, great question, honey.
Thank you.
All right, Sean, you all set, hon?
Yeah, I got it. Thanks.
All right, here's another example. The period of a pendulum, you know, one of those things that swings, you know, for like keeping time for piano and stuff. T is the amount of time required for the pendulum to make one complete swing. For small swings, the period T is approximately proportional to the square root of L, right? The formula. So this is what you're writing for. So if we start off with the formula that you guys know, y equals kx. And now let's fill in the formula and the variables they're using. So T is, right? So here we've got T is equals, right? Proportional to, it's approximately proportional to the square root of L. Proportional to the square root of L, which is the pendulum's length. All right, this next one, we want to write a formula for this as well. An object's weight is inversely proportional. So back up here, sorry, I didn't point this out. This is the inverse formula that you guys are familiar with, right? And notice that if they say the word inverse, then you have to say, you know, it is inverse. If they don't say the word inverse, you're going to assume that it is, they're talking about direct. Okay, so we're going to start with y equals k over x and fill in what we know, right? So w is, so we know w is, right? Equals is inversely proportional, right? So the k is on top to the square of its distance, r. To the square of r would be r squared. Now, watch, this is where I'm going to try and move you over to the other, the power function. So notice that k over r squared is the same thing as k times 1 over r squared, right? Which is also equal to k times r to the negative 2. And now doesn't that look so much more like, I'm going to write, I want to use the same letters that they're using. So this is algebra 2 notation, right? And you can tell that you can rewrite it using the exponent rules, right? And then now look, it looks a lot like, let's see, f of x is equal to c, where c is now what we're calling the constant of proportionality. And then there's some base to a power. In this particular case, the power is negative, which just looking at it, you should say, oh, that's inversely proportional. That's an inverse proportionality formula. So by the end, we're going to be using this applied calculus version of proportionality because it covers both direct and indirect, right? It just depends on whether or not that the n exponent is positive or negative. But this way, we're using just one formula, which is simpler. Any questions so far, guys? Everybody okay? Okay. Okay, so here's some of the the exponent rules that I was reminding you of before, and that this one I just used just now, right? If you have 1 over a to some power, you can also write that as just base a to the negative power of whatever this number is. We use this quite a bit in this section. But some of the other rules are here too, just in case we need them. All right, so remember, power function is a function, I'm just rewriting this, that can be written as some constant times x to the p power. Same thing as what I was saying before. See, just using different variables, and you'll see that they do this. The variables I was using was f of s, be like, get rid of that. F of x is equal to some c x to the n. So they're going to give you different variables, but it's all the same thing, right? There's a constant, there's a number out front, which is your constant of proportionality. And so that would be both of those, right? And another thing that is important to recognize, especially if I'm asking you if something is a power function or not, is you want to recognize that the exponent, no matter what variable they give it to you in, no matter what letter they're using, the exponent must be a real number. In order to be what we're calling a power function. So it's actually a number, by the way. It can't be a variable. It's actually a number that's in there. Okay, so which of the following are power functions? For those which are, write the function in the form q of x equals k x to the p, or this form too, right? Just using different letters, and give the coefficient k and the exponent p, or in this case, give the coefficient c or exponent n. So sometimes in Wiley, they're going to put different variables in there for you. So just be ready for that. But, you know, if you have a number out front, variable, and a number here, then you've definitely got a power function. So we're going to use these rules right here to see if we can rewrite this as a power function. So we can in this first case. Because this, you can rewrite it as 5 times 1 over x cubed, which then can be written as 5x to the negative 3 power, right? Since 1 over x to the positive 3 power is equal to x to the negative 3 power, right? And again, I'm just using this rule sort of in reverse, right? Okay, so it does have a constant here. The exponent is a number, and it has a base that's unknown, right? Therefore, this is a power function. And here, if we're going to tell what the k and the p are, k would be equal to 5, and p would be equal to the exponent negative 3. And b is pretty much the same, right? You could write this as 2 times 1 over 3x, but we want the x to be all by itself. So another way you could write this is you could say, well, that's the same thing as saying 2/3 times 1 over x. So I can write this as 2/3 x to the -1 power. So my k would be equal to 2/3, and my p would be equal to -1. So that's a power function. All right, this one, you can just rewrite this as 5/2 times x squared. So that's already in power function right there. So the k value is 5/2. And, oops, and the p value is 2. So that's a power function. So here it looks like it's already in that format, right? Where k is 5 and p is x, but p can't be a variable, right? According to this up here, exponents must be a real number, right? And this has to be a number also, right? A constant number. So this is not a power function. Anybody know what this kind of function is called? What's it called when the variable is in that, is the power? Starts with E?
Exponential.
Exponential.
Yeah, exponential, thank you. So let's say this is not a power function. Because P equals X is not a real number. All right, what do you guys think about E? Can we write a radical with an exponent? Is there a way to do that?
Wouldn't it be x to the 1/2?
Yeah, it definitely would. Thanks, Matt. If you look up here, there's this rule. Oh, wrong rule. Here. So you can rewrite a radical by using this rule right here. So you can rewrite this as 3 times x to the 1/2 power. So your k value is going to be the 3, and the p value is going to be the 1/2. Just so you know, if you had, let's say you had the cube root of x squared, you would write this as x to the 2/3 power. Or let's say you had the square root of x to the 5th. You would write this as x to the 5/2, since this index 2 is implied. Oops, I should put a equals there. So these are just extra examples of using that. That rule. Okay, and now we're going to use another rule. Oh wait, did we say? Oh, so this is a power function, right? Yeah, we decided. All right, this next one, I'm going to use a different rule, different color. Here we're going to use the power of a power rule. Power of the power rule says that you multiply the exponents. Or actually power, is there a power of a product rule? Yeah, and this. Okay, so what you have to do with that outside exponent of 3 is you have to apply it to everything on the inside, right? So you've got 3 cubed and x squared cubed. So that would be 27, and then you're going to multiply these two, x to the 6th power. So what's your k value?
27,
And what's your p value?
6.
Yep. Okay, so you'll see if a good number of problems like that to get you used to figuring out if something is a power function or not. Of course, this is as well. I did update the notes earlier today, so if your notes are slightly different than mine, I wouldn't worry about it. But I just saw an opportunity to put some things in at the last minute there when I was reviewing those notes earlier today. All right. Okay, so now let's look at the power function that are all of these. The x, this is quadratic. This is cubic. This is reciprocal. This is what we call rational. And this is the square root function, right? Remember how y is equal to the square root of x? Same thing as x to the 1/2 power. So all we're going to do with these graphs right here is get you kind of familiar with concavity, end behaviors, any asymptotes, that kind of thing. Because when we start looking at applications and their graphs, it'll tell you a whole bunch. If you can look at a graph and recognize what the end behavior is, where it's, where it's concave up, concave down, and so forth. All right, so this first graph, is this concave up or concave down? What do we think?
Is it concaved up?
Yeah, definitely. All right, let's go through some of these others. This would be concave down, right? On the left side, and then concave up on the right side. On the left side, x cubed is what? Concave up or concave down? I'm talking about the left side of the cubic.
Concave down.
Yes, concave down. And while we're talking about concave up in the first one, and so it's concave up for both negative x, right, which would be the left side, and positive x, right, which would be the right side of the graph. So the quadratic is concave up over the whole thing. Another thing that is interesting or good for you guys to recognize when you're looking at graphs, especially as we go forward, is whether or not where it's increasing or decreasing. So you can say here it's decreasing. And then on the right side, it's increasing the whole way. Let me not right on. Okay, now let's talk about end behaviors for a minute. end behavior of a graph, that just discusses what the end of the graph does, okay? So if you're talking about the left side of the graph, you're talking about when x is getting smaller, right? Or going to negative infinity. The right side of the graph refers to when x is getting larger, okay? So if I ask you to describe the end behavior of a graph, you're going to include both the left and the right. So for this graph here, you would say as x gets smaller, y gets bigger, right? Because if you go on the graph this way, x is getting smaller, but y value is getting larger, right? It's going up. And so that would cover the left side of the graph. The right side of the graph says, and this is just vocabulary, right? You say, instead of saying the right side of the graph, you just say as x gets bigger or x goes to infinity. So the right side of the graph, what happens to the y value? Does it get bigger or does it get smaller? So what do we say? How do we finish this? Y goes to what? Is it getting bigger? Is the y value here, as x gets larger, is the y value going up or is it going down?
It's going up.
Yeah. So as x gets bigger on the right side, right? That's just vocabulary for the right side of the graph, right? As we travel from left to right on the graph, the y value is getting bigger. Let's see. Let's try it on this next graph here, which is the reciprocal function. As x goes to negative infinity, this is this side. So as x getting more and more, oh, sorry, wrong way. As x is getting smaller and smaller and smaller, what's happening is the y value is running into a horizontal asymptote. So that horizontal asymptote is right here at 0. So as x is getting smaller and smaller and smaller, so if we're traveling this way on the graph, it approaches a horizontal asymptote. And I don't know if you guys remember from high school, but it never is going to jump over that horizontal asymptote. What it's going to do is it's going to get closer and closer and closer and closer, infinitely close to where the y value is, where the asymptote is. So as x goes to negative infinity, you could say that y goes to the vertical or the horizontal asymptote at 0. So it never actually reaches 0, but it's going to get very, very close to 0. Now, if we look at the right side of the graph, right? So here, as x is getting bigger and bigger and bigger and bigger, it also gets really, really close, but never reaches that horizontal asymptote of y equals 0. So as x gets bigger, y is getting infinitely closer to 0. But never actually getting there because of that horizontal asymptote. All right, what else? So this is, of course, concave up. I want to finish this. And you would say that it's concave up for all of the positive x values and concave down for all the negative x values. All right, let's look at end behavior for this. So as x goes to negative infinity, this is the left side, right? So that as x is going there, does y get bigger or smaller?
Smaller?
Yeah, definitely. So you say that y goes to negative infinity, right? So notice if you think about points on this curve right here, this point right here has a negative x value, right? And then this has a negative x value, but it's also going down. So the y value is decreasing from this point to this point, right? Well, let's look at the right side of the graph. As x gets bigger, that would be this, right? The end behavior, y values from this point to this point, are they getting bigger or smaller?
Bigger,
Definitely bigger. And how do you say that?
increasing.
Yeah, but y would go to what?
Oh, infinity.
Very good. Yeah. All right, good. Okay, so let's see, concavity for this one. This is concave, up or down? Anybody?
Concave up.
Yep. So it's concave up for the negative x values, right? And concave what for the positive?
Is it still concave up?
It is, very good. That's where students have some trouble. You know, what you have to remember is that this and this together make that, right? A lot of people want to say that when they're next to each other like that, that one is concave up and the other is concave down. But you just have to remember it's halves of a U. If you can make a U with the whole thing, then they're both. Let's see. All right, so let's do end behavior for this. As x goes to negative infinity, so that's this, what does y go to?
Infinity.
0.
Yes, very good, excellent. Yeah, because this is a horizontal asymptote, right? So you would say that y goes to 0. And as x goes to positive infinity, that would be this side of the graph, y is also going to 0.
I have a quick question.
Mhm.
Can you explain again why the y asymptote would be going to 0?
Yes. Let's see. Let me use I'm going to do a different example. Let's say I had this graph that looked like let's say that the horizontal asymptote was here at y equals, let's say 3, okay? And let's say I had a graph that looked like that. So if you wanted to talk about end behavior here, as x gets smaller, right? This is this side of the graph over here, right? What is y doing? Here you would say, well, y is going to travel real close to this horizontal asymptote. Y goes to 3. So it's not always at the origin, just so you know. And then as x is getting bigger, positive infinity, that would be this side of the graph. And on this side of the graph, it's not getting bigger like this, right? It's getting closer and closer to that horizontal asymptote of 3.
Okay. I think I'm getting, yeah. Thank you.
Yeah, you're welcome. You're welcome. I hope that, I know because when I do it up here, I don't want you to think that the horizontal asymptote is always going to happen at y equals 0. It could move all over the place, right? It could be a negative number down here too, depending on what the graph is doing. All right, and do we have concave up or concave down here for this last one? What do you guys think for, this is the graph of y equals the square root of x, or x to the 1/2. So is this concave up or concave down?
Concave down.
Thank you. And it is concave down over the entire graph, right? So it's concave down. It also doesn't have any negative x values. Why do you think it doesn't have any negative x values?
You can't take a square root of a negative.
That's exactly right, right? So notice no negative x values. Because you can't take square root of a negative number. At least you can't do it in the real number set, right? In the imaginary set, you're allowed to do it, but not for real numbers. And we're talking real in this class. What else did I want to tell you? Over what interval is that graph increasing? I asked you, what interval is this graph increasing? From what to what? We know it's increasing. And if you wanted to use like interval notation to answer that question, you could say it's increasing from 0 to infinity over the whole graph. And then there's one other thing I wanted to talk about. So here you said it makes sense that there's no negative x values because you can't take the square root of a negative number. So that makes sense that this graph wouldn't start in the negative territory. Here, we don't have any negative y values. Why is that? Why are there no negative y values here?
Because it never goes across the axis.
Definitely does not. And there's a reason for that. The reason why it doesn't is because notice how 1 over x squared is the same thing as x to the negative 2 power. What happens to a negative number when you square it?
Becomes
Becomes
positive.
positive.
Yeah, it's always going to be positive, right? So it makes sense that the result of this will always be positive numbers. And remember, the results are the y values, right? So it's not, you can't square something and end up with a negative number, right? All right, cool. Okay, so now we're going to talk applications. And we're going to talk applications of linear and quadratic and even, I guess I just have linear and quadratic for you. Okay. So this is the formal definition of a polynomial. And just to give you an idea of what I'm talking about here, let's say I have, wait, I'm going to write it. All right, let's say I had something like y equals 5x squared plus 3x plus 5. So this is the formal definition of that. All they are talking about is this a is the leading coefficient. And then there's, subsequent terms. And then here we've got plus, here's 3x, and a sub 0 is referring to the constant. So if it fits that definition, then it is a polynomial, right? If you can write it like that. And notice that it's a polynomial even if it has negative exponents too, right? Okay, so this first example, a company finds that the average number of people attending a concert is 75 if the price is 50. So what they're giving you here is an ordered pair, right? So y equals 75 when x is equal to 50. What we've got here is we've got, let's say this is P. Actually, I should use P and Q. I should use P and Q. Actually, let's do this just because I think you'll get it easier first if we talk about y equals mx plus b. Okay, so and then we've got this other situation here that at price of 35, you could say that y is 120, right? 120 when x is 35. Okay, so they're basically giving you 2 points. And they also tell you that this demand curve is a line. So we're going to write the demand as a function of price. Really what they're asking you to do here is write an equation, giving you 2 points. So giving you 2 points, x and y, write an equation. So let's go back to when you learned this in Algebra 1. We've got y equals mx plus b. And they're giving us 2 points, 50 and 75, and 35 and 120. So instead of x and y, let's call this P and Q. But we're still going to use our y equals mx plus b formula for a minute. What I'm going to do is I'm going to plug in, well, actually, first what I'm going to do is find the slope. So slope is relating the number of people to money, to dollars, right? So where people is Q and dollars is P. You know, I think my dog is in my garage. Hang on a second. What are you doing out there? How did you get in the garage? Huh? She's a little escape artist. Okay, so just the slope formula, remember M? So it's just y2 minus y1 over x2 minus x1. And so we can just do 120, or we'll say this is x. No. So here's x1, y1, here's x2, y2. So we're just going to fill that in. So you get 120 minus 75 over 35 minus 50. And you'll get -3. Now what does that mean? It means that the number of people go down by 3 for every dollar difference. So you can say -3 people per dollar. Remember, we're here for the meaning, so stuff like that is important. Okay, so once we have the slope, what we can do is, let me move this down a little bit. So once we have the slope, we can plug it in here. So y equals -3 x plus b. We found the slope, then we're going to plug it into the y equals mx plus b formula. And then what we're going to do is use one of the points for X and Y. So Y is, let's say, 75. And X is 50, right? We're just using this point. And I could have used the other point too, but. So I know that this is -3 plus B. So all I have to do is solve for B, and then I'll have a whole equation that I can use. So if you simplify that, you're going to get, where am I? B, let's see, this is -150. So if you add, it's 225. So B is equal to 225. All right, so now we have our formula, right? Our formula is Y equals -3 X plus B, which is 225. So what we've done is we wrote the demand as a function of price, but they want you to use Q and P, right? So we can say that Q is equal to, well, actually, let's write it like you would if you were in Algebra 2. Q is equal to -3x plus 225. But now that we're in calculus, we write this in this new way, 225 minus 3x. I don't think Wiley, I think I was helping somebody online. I don't think that they care which one of these you use. I think we proved that, if you put it in either way, that Wiley would still accept it. But I just want to use correct calculus ways too. Okay, so all of this you guys did in Algebra 1, right? If I give you 2 points, you find the slope of the 2 points, and then use one of the points in the slope-intercept form to find the y-intercept, which is B, and then you have a whole equation, what we've just done. Okay, so now we're going to use our answer in part A to write the revenue as a function of price. Well, one thing that you do know is, we should probably say that we should make it clear. We do know that that the revenue would be the price times the quantity of people, right? And we also know that the quantity of people from up here has a formula, 225 minus 3x. So all we have to do to get a more thorough revenue function is substitute Q in for this Q. So we've got P times 225 minus 3x. And if we just distribute, we'll get revenue is equal to 225P. Oops, let's use P. I shouldn't use X. Let's use P. And actually, I should have used it up here too, sorry. This is Q, this should be P. So this would be 225P minus 3P squared. So there's your revenue function. All right, now, if you graphed this, let me see, I think I have Desmos. I think I did put this on a graph. So if you graphed this revenue function, I just want to save those other graphs for something coming up. You would get, not surprisingly, you would get a parabola upside down, right? Because if you wrote this, how we write it in algebra 2, it would be negative 3p squared plus 225p. And the negative 3 means that it's an upside down parabola. So what you're looking for here, right, is the max. Now notice that the x value is going to be price, right? Because this is the x-axis, and the y value is going to be revenue. So be careful that you're answering the question that they're asking. Here they're asking what price should be charged to obtain the greatest revenue. Was this going to be the x value or the y value? What do you guys think?
X.
Yeah, definitely the x, right? Because it's here. So if you found this max, and you can do this, you can either use Desmos to do this, or if you have a TI-80 something, you could use second trace button and then choose max. And it'll have you put in bounds left and right and get closer to it. I would show you, I used to have it on my computer, my TI-83. I used to have it here, but you know, when Baltimore County got hacked, all of my everything got lost. I can't show it to you, but I can show it to you using Desmos. So anyway, you're looking for that x value, and if you looked at it, it would be 37.5. And then there'll be another number over here too, the y value, which should be 4218.75. What does that tell you? What's the y value tell you? In words, what's that telling you?
What the revenue is going to be.
Yeah, if you charge $37.50, then the revenue will be $4,218, which notice that's the highest point on the graph, right? So where are you going to make the most money? Well, you're going to make the most money when you charge $37.50. So let's answer this question that they're asking. Any questions? Okay. Bring this guy back up. Okay, so Health Club has cost and revenue functions given by those two C and R equations, where Q is the number of annual club members and P is the price of a one-year membership. So the demand function for the club is Q equals 35.50 minus 27P. So this is what we do. Use the demand function to write cost and revenue functions as functions of P. So what we do is we start with the cost function, which is 10,000 35Q. I'm just getting that from right there. Oops, it should be plus 35Q. And we're going to fill in what we know. 10,000 plus 35 times, we know the Q is here. So we're going to put this in here, 3550 minus 27p. And then we're just going to simplify that by distributing here and here. And if you did that and added like terms together, you're going to get 134,250 minus 945p. So there's the cost function. We're using the cost and the demand function to find out what the cost function is in terms of the Q. Okay, so that's one part of it. Now let's do the other part. This is a revenue. Revenue is always going to be the price times the quantity. So revenue equals price times Q, which is 3550 minus 27p. And if we simplify that, we get revenue is 3550p minus 27p squared. Okay, so if we sketch a graph of this, the revenue function would look like a parabola, which makes sense, right? Because this is an upside down parabola, right? And it's a quadratic. This is linear. Okay, so the cost function, I'm going to make the cost function pink here. The cost function is going to look something like a straight line. Let's say something like this. And that should make sense to you too, right? Because the slope is negative, right? So that's what the graph is going to look like. Now we're going to take a couple of points here. We're first going to answer this question. When does the club make a profit? What you notice, let's see here. Oops. Uh-oh. There we go. Okay. Is that this part of the graph, you can say that the revenue is greater than the cost, right? For all those points. So we need to know what those points are in order to determine when it makes a profit, right? So let's go to Desmos. And here's my graph. So this is the part where, let me make sure I'm graphing the same thing. Yeah, cost and, yeah, good. So this right here, this point right here is 39. Let's just round it to 39, right? This point over here using Desmos is, what did I say? Yeah, 127.47. Okay, so this is where I'm getting these numbers and the notes here. So what I can say is here, that this is about 39, and this is about 127. So you can say the club makes a profit when it charges between 39 and 127. And just watch where Wiley wants you to round to. So just watch that. And that's because revenue is greater than costs. on these points. Okay. Now it says, what is the annual membership fee that maximizes profit? So the one thing that you want to do is know that when you're maximizing profit is when the difference between revenue and cost is the greatest. So what you're looking for, although you would think that you would want to just go to the max, right? If we chose this point and just said the max, then this is the difference between profit and cost, right? Or sorry, between revenue and cost. But what we really want is we want that line that I just drew to be the longest line that you can draw in that area. But it turns out for this one, you see how that line's longer? That means that the difference between this revenue and this cost is more, right? So when the difference between revenue and cost is the greatest, that's when you make the most profit. So if you're looking on your graph and on Wiley, you'll have to look like where is the biggest difference, and you'll have to look at it and say where's the biggest difference. Or what you could do is you could plot a couple points, you know, like this point right here turns out to be something like 83 and 108,421. So if you weren't sure if it was that point or not, then you could calculate a couple of points, right? The X and Y values, and you want the biggest difference in Y values. But you can also just eyeball it, honestly. Let me go back to Desmos. Let me answer this question too, right here. What's the annual membership fee that maximizes profit? It's when the difference between this Y value and this Y value is the greatest on the whole graph. And it turns out to be about right here. So you would say, the membership fee of, what did we say it was? Oh, 83. Maximizes profit. So let's go back to Desmos. So let's see, what did I say? It was somewhere around 83. So let's say right there. So the difference, the distance from here straight down to here turns out to be the longest you can make. The biggest line that you can make from there to there. And just looking at the graph in Wiley, you'll be able to estimate it. And they give you a margin of error too. So like if you said 85, that, you know, and the real answer is like 83, that they give you a margin of error to, you know, get somewhere in the thing. Just whatever you do, don't choose this automatically, because it's usually somewhere else than the actual maximum. Okay, well, that was exactly on time today. Yeah, so I want to say something else though about this graph. This graph. Okay, so let's talk for a minute, like just two more minutes of your time. This is trying to get you like to understand what's really going on. Notice, like, let's say that we decided to charge $39, right? You would think that a lot of people would sign up for $39 memberships, right? You'd get more people to sign up, right? But the problem is that the money raised, because the price was so cheap, is not going to be as much as it would if you're maximizing profit, right? And the same thing goes for this other side, right? If you charge a whole lot of money for memberships, you're going to make a lot more money, but a lot fewer people are going to buy your memberships, right? So again, although each membership is more expensive, you're not going to make as much money as you would if you maximize your profit by looking at the graph and finding out where is revenue greater than costs, and then finding the biggest spread you can between the Y values, right? Between the revenue and the cost, the biggest spread you can, that's your sweet spot. That's what you want. All right, guys, I'm going to print these out and I'll post them to Moodle. I'm working with so many different platforms right now. Yeah, Jadelle?
So 1.8, the little your answers, like your notes you wrote, isn't uploaded yet. It's just like the outline. So the written has been uploaded.
Yeah, thank you. I'm sorry. And if you guys see that, just text me. Okay. But thank you. I really appreciate it. I'll do it right now. All right, guys, you're out of here.
Thank you.
You're welcome.
Thank you.
All right, have a great weekend.
Thank you.
See you next week.